Hi, everyone. So this is the first in a series of perhaps supplements that I'm going to record on specific topics. Maybe help clarify some things or um, add a little information. So today's topic is cutoff frequency. Okay, so this is a term that we use frequently in the field of signal processing, right? It's part of the language of signal processing, so you should certainly be familiar with it. Um, so what do we mean by that if you're not familiar with it? So conceptually, it's just meant to communicate some information about, usually in the context of a filter, which is a system, right? A linear shift invariant system, perhaps. And so if I was to have a system and I kind of draw its, I'm going to use magnitude response here. So for the frequency response. And let's say this is a low pass system. So maybe I'll just use a different color there. And so its frequency response is something like that, we'll say. Okay. Oh, and by the way, right, this is the frequency axis. Okay. So what do we mean by cutoff frequency? Well, the cutoff frequency represents somewhere, some frequency that describes where on the frequency axis this system's response is transitioning. Okay. And just to kind of throw out a few other terms that we will use. So we have a range that is called the pass band. In other words, those frequencies the system has a relatively high response to, and therefore it passes those frequencies through the system. And then we have another region that's called the stop band. Okay, and so the pass band is basically roughly there. The stop band is the range of frequencies that are basically stopped by the system or relatively attenuated. Okay, and then somewhere in between there, you have a region that you would call a transition region. Clearly, it's a transition between pass band and stop band. Okay, so conceptually, those are kind of regions of the frequency space that we might use to describe a filter or a system that we're designing. Okay, now, by the way, right, if you know these concepts apply, even if you have a different kind of filter, right? So let's say you have a band pass filter. Similarly, a bandpass filter might look like that. And so, you know, its pass band is in the middle and it has stop bands here and here and two transition regions. Okay. So those concepts apply to all different types of filters. Okay. Now, so the cutoff frequency, what the cutoff frequency is supposed to represent is to give you some idea about where the transition is happening along the frequency axis. Okay, and so it describes a frequency so let's just say cutoff. Okay, the cutoff describes a frequency at which this thing is transitioning from pass band to stop band. That's conceptually what it means. Now, there are a lot of different mathematical definitions for cutoff frequency. Okay, so understand that, you know, in different publications, different people using it, etc., might use different mathematical definitions for where to put the cutoff frequency on a filter. Okay. I'm going to talk about that a little more in a second. But just note that, you know, all of these terms, cutoff frequency, pass band, transition region, stop band, are all, you know, well, they can be specifically defined, and in some contexts, they need to be specifically defined as to what you mean by those things. But barring that, you know, they're just concepts that more or less, you know, describe parts of that filter response. Okay, so now let's talk a little bit about a specific mathematical definition. So the specific definition that I tend to use, but it's not what everyone will use. Okay, so let me draw another filter function here. Okay, and I'm actually, this time I'm going to use magnitude squared, okay, which again is, you know, if this is a monotonic function like that, shaped like that, this is going to look pretty similar. The numbers will be a little different, of course, but basically it'll be a monotonic decreasing function also. Okay. And so let's say, I'll use red for this one. Let's say we have a low pass filter. Okay. Now, let's also say, let's see. That this value, well, we will basically draw a line here. Let's do that. And say that that level represents the maximum value of that. Now, that may not occur at frequency 0. Okay, I've kind of drawn it this way so it does, but that's not necessarily the case. Okay. Okay, and so basically, here's what we're going to do to define our cutoff frequency. We're going to take 1/2 that maximum value and find the frequency at which that occurs, and that will be the cutoff frequency. Okay, and so this is basically my mathematical definition that we will generally use. Okay, and this is the definition that is used in assignment 1. And as noted, not everyone will use that same mathematical definition. Okay, so just do be aware of that. The other thing to be aware of is that this maximum value isn't necessarily 1. Okay, it's not necessarily unity, and so this, if this is not unity, this is not a value of 1/2. Okay, now in a lot of filters that might be a 1 maximum value, in which case you would use 1/2 here, but that's not necessarily true. Now, if we have And so the point here is, okay, if I have a filter function and I need to find a cutoff frequency for that function, I form magnitude squared for that frequency response. I find the maximum value. I solve for the omega frequency at which the filter function is half of its maximum value. Okay. Also notice that this will apply not just to low pass filters as I've drawn it, but also to high pass filters. Okay, so if we had a high pass filter instead, that kind of goes up like this. This definition still applies. We find the maximum value, we find half of it, and we can describe the cutoff frequency of the high pass filter in that way. Similarly, with our bandpass filter example, a bandpass filter should have two cutoff frequencies. And so, omega C1, omega C2, and that's how we would describe those. Okay, what's the import? Well, among other things, the importance of this in kind of the language is for you to be able to communicate a lot of information very quickly and say, okay, if I describe to you a system by saying, well, it's a low pass filter with a cutoff frequency of 200 radians per second, you don't know everything about that filter, but you know a lot. And you could, sketch a pretty quick approximation of that, right? If this is the frequency axis, I would basically say 200 radians per second, and h of omega quantity squared, and I'd say, okay, then it would probably look something like that. 200 radians per second is somewhere where that thing is falling off. And, it could, and, the point is that, yeah, that describes almost everything you need to know, not exactly everything, because it might, there are a couple of variations on that could still have the cutoff frequency, right? You could have something that kind of goes like this, or close to that, as I have drawn. But knowing the type of filter and the cutoff frequency or frequencies lets you draw a picture in your head of what that is and communicates almost all of the information about how it's going to perform. Okay, and so that's why this is important in kind of communicating in this way. And so even if somebody uses a different mathematical definition of cutoff frequency, you can still count on that's roughly what it means, right? Again, it means that, well, this is where the filter is transitioning. So, maybe we know that. Okay. Oh, the other thing I will say is that sometimes an alternate name for this is corner frequency. And so you see some people use that. I don't, but some others might. So that's our discussion of cutoff frequency. And I hope that helps you a little bit, maybe on the homework. And I guess we'll cut it off now. Thanks. Bye.